Is life fundamental in the cosmos? By this I mean, is life an inevitable outcome of the development of our universe baked in from the beginning? One need not believe in God or in anything supernatural to give credence to the big speculative idea that life in our universe is no accident, that life somehow must emerge from the deep structure of the cosmos. How to address this big question? One way is to examine the deep structure of the cosmos and to do so via mathematics, which is the foundation of physics. Here's the question that follows. Is mathematics also the foundation of biology? Can mathematics explain biology? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. How to explore the relationship between mathematics and biology? First, mathematics can describe biology with simplifying models that approximate reality. So, how does this work? Second, can mathematics also constitute the biological mechanisms that are reality? I start with state-of-the-art research. I meet a pioneer who develops mathematical models to assess physiological disorders. What do these models say about the mathematics of biology? The author of From Clocks to Chaos, The Rhythms of Life, Leon Glass. Leon, I'd like to understand how mathematics can help elucidate the rhythms of life.
So one of the ways that the mathematics has interacted with the subject matter is to develop mathematical models of the various systems of the body, the various rhythms of the body, in nerve cells or in heart cells, the various ionic currents that are going into and out of cells. All of these are described experimentally. You can measure the velocity of a conduction of a nerve cell. You can measure the period of the heart. But you can also try to study the underlying mechanisms and develop equations that one can use to model and to reproduce the behaviors. So one of the ways in which this has been important is in terms of making the experiments better. In our own work, one of the problems that we're very interested in is predicting the risk of sudden cardiac death. One of the factors that plays a role is instabilities in the heart that may be observable and may be understood prior to the cardiac arrest. It has been documented, mostly in early work, that abnormal beats called premature ventricular complexes have increased the risk for sudden death. When we look at electrocardiograms, when we look at records of heartbeats over people over many hours, and people particularly who have these abnormal heartbeats, we see extremely unusual patterns of activity, which are almost like fingerprints. We call them heart prints, in which individual people can be distinguished one from the other. Well, we believe that some of these dynamic patterns may be significant in terms of increasing or predicting the increased risk of heart death.
And what type of mathematics do you use for the analysis?
So most of the analysis at the moment is just statistics. If we try to do models, then the models are using either difference equations or nonlinear differential equations to try to model the details of those dynamics. But we have found it very hard to model the details in individual people. This is frustrating,
right?
Because it's the sort of thing that we ought to be able to do. So one of the problems in this area is that the real world events in any person are comparatively rare.
Right.
So it's necessary to develop big databases over long periods of time.
Right.
And I might say that one of the ways mathematics is being used now is in terms of development of large databases to try to make sense of what's happening in individual patients. So one of the ways in which things will go forward in the future is developing increasingly personalized models for understanding what's happening in individual people and also predicting what will happen.
Leon's work exemplifies two kinds or uses of mathematics in biology. First, statistical analysis of large data sets. And second, model making to improve experimental design and enable individual predictivity. For example, that cardiac arrhythmias may be dynamical diseases offers new treatment protocols. Clearly, math and biology are related. I'm not surprised, but it's the scope and kind of relationship that count. The more pervasive and powerful math is in explicating biology, the more fundamental math may be in driving biology. So, can math also explicate other areas of biology? Take biological reproduction, such as the spread of infectious diseases. I meet the scientist who initiated the field of virus dynamics, which led to a quantitative understanding of HIV infection, professor of biology and mathematics at Harvard, Martin Nowak.
So mathematics can be used to describe populations of cells and viruses. Viruses infect cells, and infected cells produce more viruses. This is what I call the basic model of virus dynamics, and that's a very simple mathematical equation. And that's an equation you can actually use to really address a very important biomedical problem, and that was something that we did in 1995. For example, HIV, anti-HIV treatments already became available. Yep. And you gave a single drug to a patient, and the patient developed resistance within 4 weeks. Why was that evolution of resistance so fast? Some viruses infect cells, and then they sit there, they do nothing for a very long time. So we were actually able to analyze data at that time using the basic model of virus dynamics, data how the virus abundance in a patient declines in response to treatment. So you have somehow an equilibrium of virus abundance in that patient, then you hit the virus with treatment, and then you observe how the virus responds to that treatment. And from that response rate, you can prove, actually using the basic model of virus dynamics, that generation time of the virus in those patients is approximately 1 day. In other words, 99% of the virus particles that you find in the blood of patients came from cells that were infected only yesterday.
Wow, wow.
And that you can show mathematically with the model of virus dynamics, you get this interpretation, and then you know that's the turnover rate of the virus, then you can calculate its evolutionary potential, and then you are not surprised that it gets complete resistance against a single drug in 4 weeks. And that was a very strong argument to move the field to combination treatment. So when you now hit the virus with 3 drugs at the same time, chances are that the virus does not come up with resistance because the resistant mutant to all 3 drugs is not present in the virus population at the time you start treatment. And now I'm arguing the same for cancer treatment. In some sense, it is always like this. You give a treatment, the resistant mutant is already present at the time you start treatment. This is how the biological population kind of works. The mutants are just sitting there, they're not doing anything. Yeah. But once you give treatment, you hit the sensitive cells, but the resistant ones start to grow.
Right, sure.
So we proved also for cancer that against single treatment, it is a mathematical necessity that the resistant mutant cells will be present at the time you start treatment. And therefore, you have to use at least 2 drugs at the same time. You have to force the cancer to make 2 mutational steps, each one with a probability of 10 to the minus 9, because that would not be present.
So 10 to the minus 9, if you only have 1 of them, if you have a large number of cancer cells, it'll happen.
Exactly right.
But 10 to the minus 18th will not happen.
Yes, exactly.
What kind of equations describe this?
Branching processes, for example. So these are particular stochastic processes in probability theory where a cell can either die, or it can reproduce, or it can produce a mutant, and that's what we follow over time.
And do you have to do simulation runs?
We can do computer simulations, but we always want to prove mathematically.
And what are the fundamental implications of this for therapies?
I think that you get a precise quantitative mathematical understanding of how to... Why is the gravity? A startling medical breakthrough. The cocktail of drugs to treat HIV and stop AIDS
transforming a death sentence into a chronic condition that can be managed. And key to developing the treatment is the mathematics of viral dynamics, biological secrets encoded in the language of mathematics. More clues to math's deep presence in the foundations of life? More evidence is needed. What else in biology can math explain? Can simple mathematical rules govern diverse biological phenomena? I go to the Santa Fe Institute, the world leader in complexity research, much of it based on biology, to meet a pioneer in universal scaling laws, physicist Geoffrey West.
It's mathematics which expresses the underlying generic constraints of networks. And there are concepts like the idea of space filling, which is that this network has to go everywhere. Every cell has to be fed. So you have to put that into a mathematical framework. You have to mathematize that. You have to also mathematize optimization, the fact that the circulatory system that we all share, we, in this instance, meaning every single mammal that has ever existed, we all share the same fractal-like, self-similar network, which is optimizing in terms of the amount of energy that is being dissipated in the system. So you have to put that into mathematics. And there are well-known techniques for doing this in the guise of field theory and Euler-Lagrange equations, which is in a certain sense mathematizing life. And it is from that, putting these concepts into mathematics and solving the equations, that shows, for one thing, that the optimal configuration of the network is that it is like a fractal, that it is self-similar, it sort of repeats itself with generic rules within the network itself. So the way growth works in this framework is that, first of all, you have to have the idea that you have to supply energy. So you eat, you metabolize the energy, and then you have to send it through the networks. So that's where the mathematics comes in, the constraints of the networks. It then gets delivered to the cells, so you have mathematics there. And at the cellular level, that energy, that metabolic energy, is allocated between repair, maintenance, replacing cells that have died, and so on, and new growth. And so one has to write down the mathematics of that with the network constraining it. And if you do that, what comes out is something very satisfying, and that is that you show that the growth curve, that is how the size of the organism changes with time. And what you find is something that's called sigmoidal growth. You start quickly, and then you stop. And what is beautiful about the theory is that it explains naturally why you stop growing. And that stopping of growth is intimately related to the fact that metabolic rate, the supply of energy, is scaling with an exponent which is less than 1, with an economy of scale, so that the bigger you are, less energy is being delivered to cells as you grow. On the other hand, the number of cells is increasing linearly. And if you increase linearly and you're only being supplied with something that's less than linear, eventually you stop. And that's how you stop. And use that, you can calculate the complete growth curve of any organism.
And you can use the same mathematics and come up with approximately the size of the optimization of each organism.
Yes.
So
exactly.
that's really remarkable.
So it's very lovely. And in fact, even more beautiful, I think, is that the theory then tells you how to rescale the size and age of every organism so that it appears that every organism is growing at the same rate. Everything reduces to a single curve on which we all sit. So it's the great unity of life.
Here's what's remarkable. Mathematical models not only can account for specific biological phenomena, but can also unify diverse biological phenomena across radically different life forms. Mathematizing life. The beauty of mathematics engendering the beauty of biology? Not quite, because everything I've heard so far is about the descriptive power of mathematics in biology. Can math go further? Can math discern deeper laws generating or regulating life? I ask a theoretical physicist whose creative, sometimes startling ideas challenge current belief in biology as well as in physics, Paul Davies.
What I see as being a useful application of mathematics in biology is in reconstructing the tree of life. And so if you pick a particular one of your genes, chances are it'll be identical in me. But if we look at a chimpanzee, we'll find the same gene, but there'll be a few variations. In a pig, even more variations. A geranium, even more. And so by looking at the genetic distances, the deviations, how great they are between organisms, you can go back and construct a tree and infer something about the sequence, genetic sequence in the common origin. And that's been very useful. It is a way of approaching the theory of evolution in a more mathematical way, but it's really a form of curve fitting, I think. It's not a law. There's no way, for example, that we could predict now, if we came back in another 10 million years, that some new type of organism, which hadn't existed on Earth before, would have come into existence. There's too much contingency.
You've been trying to search for new laws of physics to explain biology. If that quest turns out to be fruitful, which is very much uncertain, do you see that being described in mathematical terms?
Oh, very definitely. So I have in mind, with the new type of physics that I think operates in living systems, that there will be equations to write down that would describe it. I have a hunch that it might have something to do with the transition between the quantum world and the classical world. And so I'm about to make a very heretical statement, that when we talk about evolution in the context of quantum physics, what we mean then is not biological evolution, we mean how does the wave function change over time, how does it evolve? And there is a particular mathematical way, it's called unitary evolution. It's a bit like something being time symmetric or reversible. So long as you don't make a measurement, that's how wave functions evolve. If you make a measurement, they evolve in a very different way, sometimes called the collapse of the wave function. Some people don't believe it really happens, but that's a different story. Yeah. So I think there will be an additional term in the Schrodinger's equation for the evolution of the wave function, representing the type of biology that I'm talking about. This will be a term that would be negligible at the level of atoms and small molecules, but would become more and more significant at the level of large molecules. And this would be a non-unitary evolution of the wave function. So this idea of the wave function collapses, I think there will be this additional term which will bring the classical world into being at about the same transition as to where we would start using biology language of signals and information and translation and transcription and all those sorts of things biologists love, and the realm of atoms and molecules that physicists love.
You would not be upset if I classified that idea someplace between radical and bizarre?
Yes, I myself would describe this as more than radical, because it is a step. It's a big step, and I've resisted that step for most of my career. I've somehow thought that in my emergence view of the world, that the only real laws are the laws take place at the bottom level of physics, and that recently, because I think we're never going to resolve this dispute between emergence and reductionism. We just go on talking in philosophical terms forever and ever. And as somebody boldly says, look, there are actual genuine physical effects that could be measured where, to put it very bluntly, that if you're a complete reductionist, an atom that would have done that does that as a result of these additional effects.
And you can define that mathematically, you think?
I believe that we can define it mathematically. I have some ideas about how to do it, but unless you can explore it experimentally, then these are just just words.
Paul offers fearless, radical science, new physics with new mathematics needed for life, an additional term in the Schrödinger equation in quantum mechanics needed for evolving the waveform in biology. Yikes! Ask most scientists, Paul's conjecture will not score well. Ask me, well, I'm intrigued. I'd follow Paul along this trail, take a chance. I might like or hope there is something special about biology, not reducible to standard model physics. But what I might like or hope should not determine what I should think. I now look to the future, wonder what's in store for the mathematics of biology. I seek a visionary with depth in mathematics and breadth in biology. I go to the Institute of Advanced Study in Princeton to meet its director, at the time, theoretical physicist Robert Dijkgraaf.
I think in terms of the mathematics in biology, we're still waiting for the big breakthrough. I think physics, before Newton and others, it was also struggling. In fact, Newton had to think of the concept of a derivative, an infinitesimal change, very strange concept, and had to invent calculus as the natural language for physics, and then it turned out to be very successful. We have seen other things. In quantum mechanics, we had to think of abstract algebra and non-commutative objects, or Einstein's in terms of curved spaces. We see time and time and again when science meets a new field, a field of great complexity, with lots of data and structures, then ideally new mathematical concepts emerge. So I think the life sciences will be a great gift to mathematics, because it's a completely different world. It has a different language. What we are looking for are new ideas. And I think actually that in some sense the deep ideas from computer science, the way you think in terms of algorithms, where you have instructions that reproduce itself, that's an element that's much closer to the nature of life. I think we see time and time again now examples where you have massive data sets, and inside these huge spaces of hundreds of millions of dimensions, there are structures that you are guiding towards. And that's what we see with life. It has this massive amount of complexity, but it's channeled through somehow fixed pathways. And I think that is something where we're still lacking the mathematical language. So the amount of data that's currently being gathered in the life science, I think it's almost doubles every 6 months. I think that actually is something where new kind of mathematics could emerge. What I find so exciting is that I would see this like this tremendous transition that we're going through in science now, that we found the building blocks of matter and also the building blocks of life. And now the question is, what can we build out of that? So talking about infinite universes of possibilities, and somehow life is finding its way through that infinity. What are somehow the calculations that life is making when it builds a protein, when it builds a cell, when it builds an organism? It's such an efficient computer that I think this kind of information processing point of view will be extremely promising. And I feel in some sense now scientists are becoming designers or artists. If you're an artist and you put a pen on paper, then immediately you have a shape that has never been made before. And so what are the ways that guide you in finding interesting shapes? As a modern life scientist, as a quantum material scientist, as an information scientist producing artificial intelligence, all of us become essentially artists, trying to find our ways in this vast space of possibilities.
This vast space of possibilities, what a wonderful way to portray life. What an open invitation for mathematics to engage with biology. Mathematics, of course, is increasingly engaged with biology. Statistics are certainly essential for analyzing population data. Mathematical models certainly improve experimental design and enable individual predictivity. The deep question is whether mathematics engagement with biology goes beyond sharper statistics, closer models, better experiments. The deep question is whether the mathematics of biology goes to fundamental realities. Start with this. mathematical models reveal remarkable common principles that unify biological phenomena across radically diverse life forms. Then this: could biology as a wholly different world be a great gift to mathematics? I cannot dismiss the big speculative idea that life in our universe is no accident, that life is fundamental, and that radically novel mathematics might exist at the level of life and exist nowhere else. Could biology be fundamental, something like physics? I cannot go all the way with Paul Davies, although I am tempted, and I do hope Paul is closer to truth.
For complete interviews and for further information, please visit closertotruth.com.